wonderful. That's absolutely awesome.
Success.
Success. So let me introduce Erickson Tjoa from the University of Waterloo in Canada, who's visiting us yesterday and today. And he's like almost a leader in the field of like doing relativistic quantum information in many readings. And today we'll talk about the topic of that kind when he's talking about the Fermi two-atom problem. So thanks for coming. And the stage is all yours.
Okay, so thank you very much, Jens, and everyone who's for having me here to give a talk this morning. I'm Erickson. I'm from University of Waterloo and Institute for Quantum Computing. I'm on my final year of PhD, and I'm going to talk about this cute little project that I did on my own for the first time in my life. And I like it because it's simple. So if you get away thinking in hindsight that this project, this problem is trivial, I think I succeeded. Yeah. So let me, and I want to address some elements of the problem that I hope is of interest to some people here, because like I think many of us agree that we hate integrals, right? So okay, let me click. Okay, so in one side, this is the problem. Fermi two-atom problem was historically just a question whether the quantum electrodynamics is relativistically causal. And you might wonder, like, well, if I have quantum field theory, why would I even ask this question, right? And the answer is because quantum electrodynamics was originally an interacting theory. You don't have Green's function, you don't have anything. Basically, there's no obvious way apart from doing scattering calculations to check what you are doing. So back then, it was just not obvious at all. And this was, and the picture that they had back then in 1930s was the following: if you have two observers, I renamed it Aldis and Beatrix from a game that I played on like in my computer. And the idea is that if they are space-like separated, then in principle, if you prepare A to be in the excited state and B in the ground state, and there's no photons anywhere, so electromagnetic vacuum, you ask what's the probability of the excitation being swapped into the other atom, right? And causality means that if they are space-like separated before the light crossing time, the probability should be 0, okay? And of course, in this case, since your electromagnetic field is a massless field, when they are now separated, causally connected, then the probability can be non-zero afterwards. Okay, so that was the original formulation of the problem. Okay, you realize there's a typo here. I use a cat, but here I use density matrix, so please forgive me about that.
We can forgive you.
Yeah. Yeah. Okay, so Fermi, Enrico Fermi in 1932 claimed that QED is causal. Of course, everyone is happy, right? So the transition of probability of this sequence of operation is 0 when B is space-like separated from A. Okay, and the intuition is really sort of like a nice intuitive one, right? The B can only be excited if it absorbs photons emitted from A, because nothing else exists, right? In a way, this is the reason why you say electromagnetic vacuum, because there's no photon everywhere else. Okay. Okay. This one is a spoiler, so I should actually remove this one. This is another. So, no pun intended. This is QED done. Okay. So why would you go further if it's already causal? Okay. Now, if you have any suspicions at this point, please hold back your suspicions, because I think remember that this is 1932, where people still didn't understand quantum electrodynamics. So this is pre-renormalization era. Okay. So the question is it really QED? Okay, I put a question mark there. Okay, and then one Russian physicist came in. And he says that, okay, Fermi used one particular approximation to make the calculation work. I'm powerful enough to not use it and still do the computation, and let me do it. Okay. And then he showed that, oh, it's acausal because the probability before the light crossing time is actually not 0. So in principle, that means you have superluminal signaling. Okay, we're in trouble now. Okay, that's 30 years.
Can you say more about the kind of approximation done? Because I mean, in principle, I mean, it's an approximation, right? So there's nothing flawed about using an approximation that doesn't fulfill the
exactly.
like the exact causality.
Exactly. So back then, but this is kind of ironic because usually in the modern context, right? Usually when you use something like a rotating wave approximation, actually you typically will break causality. So this is the opposite. So when you use the rotating wave approximation, you get the causal behavior. So back then it was also not even understood that it's called a rotating wave approximation. So it is really a modern context that we start to kind of understand this in principle. Yeah. But you are right. It's basically you have to be careful about approximation. But back then people's hands are tied. Okay, people didn't know what to do with any of the computations. Okay. And between the 60 years between 1932 until the 1990s, actually everyone is divided. Okay, and if you think about it, 1990s is when we basically almost understood everything and maybe minus the Higgs field and stuff, right? And some people use specific models, and depending on what models you use, you can get causal behavior, you can get acausal behavior, and you will see a little bit of an example later. And some people use a bunch of approximations, some of them work, some of them don't. And then if you want the laundry list of it, please take a look at Hagerfeld's 1997 paper, technically an archived manuscript because he's just writing for fun. Yeah. Now, Hagerfeld was technically like a mathematical physicist. Okay, so he claimed that it is not causal, and the only thing he makes is a minimal assumption of the Hamiltonian being bounded from below, and just some extra stuff. He doesn't even make any assumptions on the models and everything, and he says that this thing is actually acausal, and he's a mathematical physicist. So the physicist, yeah.
I'm not following because I mean the argument made before is like based on a specific approximation in a specific setting, so they make a computation, a calculation, right? Whereas the Hagerfeld argument isn't that just a kind of an ad hoc argument that is valid for families of problems and for families of Hamiltonians somehow?
For Hagerfeld's one?
Yeah.
For Hagerfeld's one, yes, he just claimed that so long as your Hamiltonian is bounded from below, this will fall through.
Okay.
Okay, but the problem is the details surrounding what that calculation entails is the tricky bit.
Yeah, and that might well correspond to Hamiltonian that's just not bounded from below, right?
Yeah, it might be. And the question is whether he actually does this for spec.
Okay.
Like he's just using the QED Lagrangian, basically. Yeah. Now, Buchholz and Ingwasser, another two mathematical physicists, just few months later, actually wrote a reply. Oh, by the way, both of these are in PRL. Okay, it's kind of funny that you just reply a few months and then both of them just got into PRL. And they say that Hagerfeld's argument is flawed. And the reason is because Hagerfeld's constructions, the way that he wants, so from the minimal assumption of the Hamiltonian, and he wants to argue that it is acausal, that few steps in between requires something like an impossible measurement. So for example, you have to do projective measurement on the entire spacetime. That's one example. And or you have to do some stuff that is basically these two people are algebraic quantum field theory. To them, everything is about algebra of observables and expectation values. It makes no sense to talk about Born's rule. So if you do Born's rule and you do projective measurement and you get acausal behavior, that's not the problem. Okay, because you are doing something illegal. Okay, so that's what they are saying. Now, 3 years later, Hagerfeld replies, "Oh no, you have a problem." Okay, and the argument is because if you only believe in expectation values is technically the thermodynamic limit. You're taking n goes to infinity. So if you only do like 100 experiments, you're gonna have deviations away from the mean. And therefore, they are saying that if algebraic quantum field theory people want to make their case, they have to also bound the causal behavior with respect to the statistical fluctuations, the second moments of the expectation value of the observables. But the problem is, Hagerfeld claims that AQFT as a theory doesn't actually provide you those bounds. So you have to put those arguments on top of AQFT. So AQFT on its own cannot solve this problem. Okay? And the fight goes on until 2000. People decided that, like this argument is sort of not very good. So people start to go back to specific models and check if it is causal or not. And one thing they understood in the early 2000s was that one, if you use this thing called Glauber photodetector model, it is acausal. And it has to do with the fact that there is a rotating wave approximation built in. Okay.
And to be sure about this first take a moment, it's actually I published myself about this causality thing some time ago, which is, I mean, with this first moment thing, you basically say that you kind of integrate, like you have a kind of a point some like distance far away, and then you kind of integrate over the entire space, and then you say that the first moments are bounded from below. But you said this is not enough because it could be that it's a tiny tail, there's no information content, and then on top of that, you would want to bound the second moments from below. And you mean like the integration over space, is that right? Because then that would be true. That there's settings which have a non-negative, a non-zero first moment that have no information content because it's a tiny tail that goes to infinity. That has no.
I believe Hagerfeld wants that kind of argument.
Yeah, okay.
Yeah, but everyone else thinks that's asking too much.
Okay, good.
Yes. So Hagerfeld does want that you to capture the variances of any computations you do, and any violations of causality has to be compared with the statistical fluctuations. If the fluctuations win over, you can't say anything. Okay. And then there's this model called the point-like Underwood model, which is part of the stuff I'm going to talk about today. It is proven to be causal, but of course, this is for derivative calculations. But in any case, I hope I convince you that even though this problem is supposed to be like trivial to state, and supposedly if you believe in relativity, it should be like not even a question to ask, but it turns out that people are still fighting it today. Okay, this is a remark slide, and I think it's important. First of all, is that Fermi made this problem when we didn't understand quantum electrodynamics. But until now, we still didn't really know quantum electrodynamics because really, if you think about it, Hagerfeld is asking the full quantum electrodynamics to be causal. But Hagerfeld doesn't actually know how to describe a hydrogen atom interacting with an electromagnetic field, how to write the hydrogen atom as a quantum electrodynamics. You have to reduce this to Schrodinger equation with a Coulomb potential plus maybe Darwin term with the spin, and then you solve the Schrodinger equation there, but that's a non-relativistic limit, right? So actually, we still don't know QED. Which means right now, we really only have non-relativistic description of an atom, and at best, at relativistic correction. So for example, the gold atom is only gold in color because of relativistic correction, otherwise it looks green. So the question is whether Hagerfeld is asking too much from physics, right? He's a mathematical physicist, maybe the mathematics got too much into it. But really, we don't really know, right? But one thing for sure we know is that no one right now knows how to write a hydrogen atom in a full glory of quantum electrodynamics. That much is true. Okay, so the implication seems to suggest that if
so can I just ask a quick question? So why is it important that this has to be a hydrogen atom? Couldn't it be an electron spin?
Sorry?
Why is it important that it has to be a hydrogen atom? Couldn't they think of some spin degree of freedom of an electron?
Technically, yes, because if you take a hydrogen atom and you take the center of mass degrees of freedom to be classical, which is what we did in a standard quantum mechanics textbook, technically the wave function is the electron wave function. So when one speaks of hydrogen atom, really you're only probing the electronic part. If you quantize the center of mass too, then that's the whole atom. But yeah, you're right. You can talk about spins and isolate them. And actually, what I'm going to talk about today is basically just forget about atom and just talk about spins. Okay. But one thing that I hope is clear is that if you want to make progress in a way that is realistic, in the sense that it's something that people play around in the lab and stuff, right? It is actually not very unreasonable to really tackle this problem properly using non-relativistic quantum system like an atom, coupled to the free electromagnetic field, which is also what people believe to do in the lab. I mean, I don't think people in the quantum optics lab think that the electromagnetic field is an full quantum electrodynamics interactive field. Okay. But then, now the question is, am I just doing quantum optics? Because if I'm just doing quantum optics, then this talk is over. Well, let me first refresh or introduce, if you haven't seen one, what is light matter interaction in the sense of quantum optics. This is one version of it, there are many of it. So the way to think about it is that you have something like an atom with many energy levels. I use hydrogen atom as a reference with the energy level spacing decreased by 1/n², but you can think anything you want. And you have light shining on it and it can get excited. And the way to describe this is, for example, to write an interaction Hamiltonian integrated over time, where there is a switching function which tells you how long you interact with the electromagnetic field. And then you have a dipole atomic. The simplest one would be the dipole interactions, where you take an atomic dipole, interact with the electric field of the system. Now, for quantum optics, usually what they call an electric field is really just a single harmonic oscillator, right? It's just the A minus A dagger component of the electric field. And how do you tell this apart? Take a quantum optics textbook. If the electric field is only a function of time, that's one harmonic oscillator. Okay? And sometimes you can extend this to a few modes, that's fine. But the crucial point is that it is really just a harmonic oscillator. Oh, but there's a vector component, so that's another, maybe a requirement. Okay? But if you think of real electromagnetic field, it better solves the wave equation. So it should have a spatial component, right? So the dipole will now have a spatial dependence coupled differently to the full electromagnetic field, the one that solves the Maxwell's equation. And now you might ask, what would the atomic dipole position dependence come from? Well, it comes from solving the position representation of the wave function. So if you split this up in the position basis, it will come out with the Schrodinger wave functions that you do in the hydrogen atom, for example. Okay, but the point is that you should have spatial dependence if you do proper electromagnetic field. Okay, and this is one paper that illustrates all possible combinations of what we do. And this is what I call relativistic quantum optics, because the bare minimum to have relativity in any of this description is better to have a quantum field. Okay, and electromagnetic field can be made quantum. Okay. The spin part. Okay, you might realize that actually the essential point of this model is really not the fact that it is electromagnetic field or an atom, but really you are coupling one kind of spin, internal degrees of freedom, coupled to a quantum field. It can be vector, it can be scalar, but you just want to couple it in such a way that the Hamiltonian acts like a Hamiltonian. So you must couple them in a way that it preserves hermiticity and everything. But you realize that you can just replace the atomic dipole, the dipole operator, with just like say the Pauli X operator. Okay, and the electromagnetic field, just get rid of it and replace it with a scalar field. So really, what we call the Unruh de Wit particle detector model since the 1970s, and with a bunch of refinements right now, is really just a scalar version of the dipole interaction in quantum optics. And the quantum system is restricted to a finite dimensional, in fact, two-level quantum system. Okay, and the one thing I should emphasize is that the duration is still there, because you still have to prescribe how long you interact, but you also prescribe the size here. Here, this function f, which prescribes the finite spatial extent of the atom, is ad hoc. But for the electromagnetic dipole earlier, this fx is obtained by solving the Schrodinger equation. Okay, so the Schrodinger equation of the hydrogen atom or any hydrogen-like atom. Okay, yeah.
So I understand you're doing relativistic quantum mechanics, but and you mentioned this Unruh de Wit detector is causal instead of the Glauber one. So when you consider something like the rotating wave approximation, are you including higher order computations here?
Higher order computations as in?
So when you do the rotating wave approximation, I mean, like another way to phrase it in quantum optics is that it's like a 0th order Magnus expansion. So you can consider like higher order terms like commutators between the Hamiltonians at different times.
Okay, I see. So actually, that is tricky because by modern standards, there are two versions of rotating wave approximation. One is when you do rotating wave approximation at the level of the Hamiltonian, in which case you have to kill any term that come with sigma plus and a and sigma minus and a dagger. You get rid of it at the level of the Hamiltonian. Yeah. But there's another version of rotating wave approximation where you only kill it at the end after you get your master equation or your final density matrix. But at this point, I'm not using any of those.
I see.
Okay, remember, this is just the scalar version of electric field. This is just the scalar version of the atomic dipole. And at this point, you have the full rotating and the co-rotating stuff, right? Because this one, remember, Pauli X is like sigma plus sigma minus. This is like a plus a dagger. So you actually have the sigma minus a and a dagger sigma plus, right? So you actually still have the counter rotating part.
I see.
Good?
Yeah, good.
Now, I will emphasize this again, that what we call cavity quantum electrodynamics is really a 0 plus 1 dimensional quantum field because you don't have the spatial dependence. So really, you are doing quantum harmonic oscillation, which is not a problem in itself. But if you want to answer relativistic questions, you cannot use 0 plus 1 dimensional theory. So Unruh de Wit detector is really changing all the non-relativistic quantum system you couple to with just a two-level system, let's call it qubit, and replace the free electromagnetic field with just a free scalar field. Okay, that's the punchline of the model. And I think this is the first time I make such a clear punchline, so I'm great. Now, the question is it just going to be relativistic quantum optics and nothing else? Right? Again, if it is, then nothing else to do. Well, I think no, because once you put qubits in two-level systems, then you can start doing all sorts of quantum information stuff with the qubit. And the quantum field theory is going to carry all the relativity for you. And I will show you how. Okay, so the first attempt of using this sort of model to answer this question was by Matthew Cliche and Akim Kem. Akim Kem is my external examiner, so I have to be careful. So what essentially they prove is that QED is in principle causal to all orders in perturbation theory. In their paper, they do it up to 4th order, but they give a prescription on how to do the Feynman diagrams and stuff properly. By Feynman diagram, they mean the fake Feynman diagram between the detector and the free field. Okay, because technically you have a quantum system interacting with another one. And what they show is that the original picture that we have here is actually the wrong question to ask. Okay, because if you, I'm not sure how many of you are familiar with like S-matrix formalism or the perturbation theory in quantum mechanics courses. If most of the time we end up computing transition amplitude means state A to state B of the whole thing. So it's a scattering process, right? The problem is that to answer these questions, you cannot use scattering process because you're gonna catch things that you are not meant to. And you will see why, if you are a quantum information theorist, then this is actually kind of like in hindsight trivial. Okay, really the right question you should be asking is that if A and B are space-like separated, then does qubit B's excitation probability depend on A at all after the interaction has happened, right? So really what you're asking is the following. Take the initial state of the whole thing. So let Alice do anything they want. Bob is in the ground state. Okay, A and B, let me say, okay? And then prepare the electromagnetic vacuum, in this case, it's a scalar vacuum, do the joint unitary interaction according to the dipole interaction earlier, and then you trace out A and the field. And then you ask, does the density matrix depend on A at all if they are space-like? Really, this should be the right question. And they, in the paper, actually, they show that perturbatively to all orders in perturbation, basically, perturbatively, the channel capacity is 0 the moment they're space-like. And I hope this is kind of like a nice indication that, you know, like we are really, this kind of approach actually puts relativity into Nielsen Chong's book, right? Usually the folklore is that no superluminal signaling, just accepted. But here is a model where, you know, the channel capacity just drops to 0 the moment you're space-like, and that's okay. But this is still perturbative, right? What they have to do is to that the channel capacity is very small, but it's for sure 0 when it is space-like. So far so good?
Yeah.
Okay.
But by the way, this is like really precisely like how causality would be phrased in terms of the Brownian bound, right? I mean, the Brownian bound would have precisely that, and you would get some exponential decaying signal propagation
exactly
outside the light cone and so on.
Exactly.
Yeah.
I mean, ideally, if you have a wave equation that defines the causal behavior, then whether you have Lieb-Robinson bound problems like Lieb-Robinson bound and stuff, better reduced to like better reduced to a connection to the Green's function of the field. Okay, let me put some like anime and meme that I watched recently. Okay, so is the cliche and Kern solution good enough? Okay, and of course the answer is yes if you are answering the original problem, because Fermi also did this perturbatively. But I would say that it is not quite, because it is perturbative. The asymptotic series doesn't converge, and also it's unnecessarily complicated. The paper is like 20-something, 30 pages even in PRD. Okay, and so I claim that in the way they all lack true elegance, but you know, like if I finish this presentation and mine is also not that elegant, then I'm in trouble. But in any ways, I put an asterisk there is because yes, contingent to all the caveats involving quantum field theory, and this will be the last slide. Okay, so let's see what the more elegant solution to this. Okay, my main goal is to convince you that you can do proper general relativistic Fermi to atom problem, so fully incur spacetime of anything you like, so long as the wave equation is well defined. And the spacetime is fixed, right? Yes, and the spacetime is fixed. So this is purely in the regime of quantum field theory, incur spacetime. I'm not doing back reactions and stuff, but I think this is good enough for our problem. And in the non-perturbative regime, it means that I don't do any Dyson series truncations and whatnots. Okay, and the tool that I'm going to borrow is a bit mouthful, but it's what my field called relativistic quantum information, and the other field, very big field called the algebraic quantum field theory. Okay, and the way I would sell this is first remind you that this was our Unruh-Lewis model, the finite size Unruh-Lewis model. Now, just group the integrals together, group the space and the spatial size and the duration together, and you realize that this whole thing defines an interaction region in space and time. Okay, so this is a space-time smearing of the interaction. Okay. Now, to upgrade this to general relativity, all you need to do is to define a Hamiltonian density, put space-time on equal footing, and put a Jacobian to correct for the volume changes due to the curvature of space-time, and also acceleration of the detector. And you realize that I've combined here the space and time smearing into just single function that depends on space and time coordinates, integrated with the original interactions. Now, the only one subtlety here is that this tau, the proper time of the center of mass of the qubit, is now possibly dependent on the space-time coordinates you use to integrate this, because of course, if the qubits move, it's going to the proper times. How fast the clock ticks is going to depend on how you move and what's the space-time curvature. But this is just a label at the moment. But there is the most important thing is that this interaction Hamiltonian in curved space-time can always be naturally prescribed by someone who is at rest, right, carrying the qubit. So if I'm at rest carrying the qubit in curved space-time, I have what we call the Fermi normal coordinates. It's the coordinates adapted to the trajectories of the observer. And in this coordinate system, I prescribe that I can always separate what's my spatial extent of the qubit and also what's the duration. So intuitively, it just means that if I do experiment in the lab, I better can tell that my hydrogen atom wave function is this, and the duration of interaction is a separate thing. Okay, of course, to an external observer who is using different coordinates, space and time is going to get mixed, so they can't split this up. But the experimenter better can do this. Okay. But otherwise, this integral, because this is a Jacobian, this is going to be covariant. That means it is independent of any coordinates you choose. Okay, so the picture you would have right now is now like a more curved space-time generalization. So now the constant time slices can be a little bit curved. It's like a Cauchy slice. And then the light cone will move in certain way according to what trajectory and the curvature. Sometimes you have problems because of similarities, but this is basically the cartoon picture of curved space-time and the light cones. Okay, and the tube is just to emphasize that you're really interacting in finite extent. Okay, now the non-perturbative one, we will use the following trick. Okay, and you'll see why. I'm going to assume that we are in a region that we can do interactions very quickly. That means we just interact with the field at just one instant in time. It's just an approximation, but pretend you can do this. Okay. And what does this buy us? Well, remember from your quantum mechanics or quantum field theory course that the root of all evil is the time ordered exponential. The moment you see this, you give up. You either spend 5 pages doing perturbation theory or just submit a blind homework. Okay. But if you do delta time interaction, you don't have to do time ordered exponential because there's nothing to time order, right? You only interact at one time, right? And if you have 2 isolated qubits, then it looks like there is time ordering, but you know how to time order them. Either Alice comes before Bob or Bob comes before Alice, and that's it, right? And so you can always write the unitary into a factor version of UB times UA, because here we are setting up Bob to turn on later. And with this approximation, you can show that each unitary is actually just a control unitary. If it does nothing to the qubit, you apply a cosine of phi. If it does something to the qubit, you apply the poly x, then you does sine phi. If you think about it a little bit, this is just this sine and cosine, right? It's actually just constructing like a cat state out of the vacuum, because sine and cosine are linear combinations of exponentials with different signs. Each of them are displacement operators. So actually you produce cat states. Okay. And phi of f is a shorthand for the smear field operator. So you take the field operator and you just integrate over the interaction region. And actually, for technical reasons, this is actually the well-defined operator in quantum field theory. So phi of x is actually an operator value distribution. So it's a little bit like a delta function. So it's not really an operator. Now, it's a little, yes.
This question, is it important that you assume that the interaction happens as a delta, or could you just assume that it happens over disjoint windows of time?
No, the disjoint is not enough, because the disjoint allows you to factorize these two, but each of them you have to do perturbation theory.
I see.
So if you separate them properly, especially if they are space-like, you can factor them out. But then each of them you have to do perturbation theory and then you are stuck. But if you do delta interactions, you can actually get a control unitary out of this. Okay. So I think this is not, I'm not the one inventing this, but I hope this sounds kind of like cute enough to see that, you know, we actually have certain regimes you can bypass the evil time ordered exponential. And then the best part of it is this. Okay. I know you just go, yes.
Yeah, I just want to clarify. So you said this field theory involved, but you seem to be using Hamiltonian the whole time. So I'm a bit confused.
Sorry?
You seems to be using Hamiltonian the entire time. So I'm a bit confused where the field theory comes from.
I mean, are you talking about why I'm not using Lagrangian and stuff?
Yeah, but you have this density. I understand. That's fine.
Yes.
But I don't see how this.
Okay.
Because I mean, I understand like Hamiltonian, they're not relativistic, right?
Yes. So the next two slides, hopefully we'll do this.
Okay. It comes later.
So one thing, like what he has asked is that you might notice that the way I introduce quantum field theory is kind of like weird, because I've just written field operators and do something, but I haven't introduced canonical commutation relations. I haven't done equation of motion. So how do you know this phi has is actually a quantum field theory, right? And Hamiltonian exists for any dynamical system. It's not quantum field theory, right? So first, let me just bring this up. So route one, if you're a hardcore physicist, you just brute force do the computation, okay? And you're done. But let me bring you to route two, which is going to take us to some detour, but it's going to bring something nice in my opinion. Is that observe that this sine and cosine are all bounded operators, okay? Phi quantum field is the field operator is unbounded, but the exponential is bounded, okay? And this is because we're in free field. And because these separately are bounded, actually each of these exponentials of I phi is actually a generator of a certain C star algebra. And this is the definition of an algebra of observables for the field theory. And this is where I come to the definition of algebraic quantum field theory in curved spacetime. So for non-interacting QFT, you can actually define quantum field theory this way. You think of the field operator as essentially a map from functions that prescribe the interactions to an operator. So by this, I mean the following. Think of the field operator as a map from a function f to a new object, which is an element of an algebra. Okay? And then collect all these exponentials together, let them generate via multiplication and stuff, and you get what we call the Val algebra of observables. It's just the algebra generated by the exponential. Of course, if you set f equals to 0, then the exponential is just identity operator, in which case this is also a unital C star algebra. Okay. And to do quantum mechanics or quantum theory, you also need algebraic state. You need a state, right? And a state is just an assignment from the algebra to the complex number, and such that it is normalized identity to 1, and it takes positive numbers for positive operators. So all this means is just that from the perspective of algebraic quantum field theory, which is what Buchholz and Ingvason advertised earlier, is that it should be all about algebras and expectation values. Okay, now how do you know that this is a relativistic quantum field theory? I'm not sure if this is going to be part of the answer that you're looking for, but essentially first we need to make sure that the phi that we are talking about is actually an actual time-Gordon equation in curved spacetime. So you actually should solve the wave equation. And since it is a linear hyperbolic partial differential equation, it admits a Green's function. Okay, and once you have a Green's function, the quantum field theory is complete the moment you define the canonical commutation relations between the field operators. So essentially, in this form, the canonical commutation relation says that the two field operator commutes to something that is proportional to the causal propagator. Causal propagator is what we in electrodynamics call the advanced minus retarded Green's function. Okay, it is the one that is supported on both the light codes. Why do I say this? The most important bit is that in quantum field theory, you always wanted this idea that you have microcausal behavior. That means operators at space-like separation commute. And you see that here, two operators commute if F and G, the interaction region, are space-like, because the Green's function integrated over those two regions are actually zero. So this is a little bit different from what you see in like Paskin and Schroeder and the standard quantum field theory textbook, because the way they do there is to slice space-times into constant time slices and then do what they call the equal time commutation relation. So you do phi and conjugate momentum pi and then commutes to I times delta. Okay, but in the more modern way of thinking about this, actually you should be thinking about local field observables and you just talk about the Green's function of the field. So they are actually equivalent for non-interacting fields, but for interacting field theory, which is not part of today's talk, actually only this way of defining quantum field theory works. Like you cannot actually define the slice by slice quantum field theory. But the box is the most important bit. If the interaction region F, the space-time smearing F, and another space-time smearing G are space-like separated, the Green's function just tells you is zero. Now, this is a big theorem, but I hope some of us have seen this in some form, that there's this famous theorem from the 1940s, it's the Gelfand, Naimark, and Segal GNS representation theorem that says that if I give you a C-star algebra, and I also give you an algebraic state, you can actually reproduce the Hilbert space representation of your quantum system. And the Hilbert space construction is going to be the ones that we are familiar with. Okay? And the way the technical term is really just that hand me a C-star algebra, hand me an algebraic state, I can always construct a GNS representation so that and also a preferred state, a vector state, so that I can reach every other state in the Hilbert space by acting on some operators. So in the standard quantum field theory or quantum mechanics, this would be the vacuum state, for example. Okay.
I think it needs to be cyclic and separating.
Yes, it should be cyclic and separating, but there's no, actually the separating part, I don't think it is needed here. The separating part is for the rich leader.
Why don't you need it here?
Because the separating part is just to make sure that the bicommutant thing commutes, right?
Yeah. Oh, right. Yes. Yeah. Okay.
Like this is already true even in quantum mechanics.
Yeah. Okay. Okay. Sorry.
So the technical term he was mentioned, Sosa was mentioning was about the vector actually is a cyclic vector. Just means you can reach every other vector in the Hilbert space by acting on some operators. Separating is actually a condition you put on a quantum field theory and sometimes in quantum mechanics where you want to make sure that certain things commute properly. But that's not the part of the talk, and I think it's not necessary for the DNS. Okay, but the crucial thing is that now in this representation, the expectation value looks like expectation value. Okay, so it's like a sandwich bracket of something. Okay, and this is essentially unique up to unitary equivalence. Okay. Now, I just want to make a quick comment in case you have heard this thing called the Unruh effect, where people talk about accelerating detectors actually thermalizes to a temperature proportional to acceleration, or the more famous one called the Hawking effect, where black holes radiate. It is actually just a statement that if you fix the algebraic state, but you consider different subregions of space-time, you actually get a different Hilbert space that is not unitarily equivalent. And this implication means that if two people think they are quantizing with respect to a vacuum, one of them thinks the other person's vacuum is not actually a vacuum. So some of them has particles. This is an aside, but I hope you will take a look at it.
Sorry, can I just pick up on your side? So which of these assumptions is violated in that in this setting where in this Unruh effects?
Oh no, it is not actually violated. The problem is that in Unruh effect, the Minkowski vacuum is you take an algebra observables restrict on the whole spacetime.
Yeah.
But for the Unruh effect, you restrict another algebra observable to the Rindler wedge. So actually, you are changing the algebras.
Oh, they're different algebras.
Yes. So this is something that I think is not very clearly described everywhere, but essentially Unruh effect is just a statement that two people use the same vacuum for two different subalgebras and they get different answers. But this never happens in quantum mechanics. This is one of the nice things I learned about algebraic quantum field theory is that finally Unruh effect makes sense. Now, the key takeaway is, however, that in what follows, the proof for the, not proof, the argument for the Fermi atom doesn't require me to specify what space-time I mean, any GNS representation I pick, and also anything else. Okay? Before we do that, we should see what algebraic QFT thing is the vacuum state. Okay? So remember, the Fermi problem requires that I have no photons everywhere, right? So I need to be in a vacuum state. Now, in algebraic quantum field theory, what is nice is that a vacuum state is what they call a quasi-free state. I asked an algebraic quantum field theorist, and he doesn't know where this terminology comes from. So I can't explain to you why it's quasi and free, but it is essentially Gaussian centered at zero. So this the coherent state is a Gaussian state that is not a quasi-free state because it's the free space is not at the center, right? But basically, Gaussian center at zero means that all the odd endpoint functions vanish, but the even endpoint functions do not. Now, in algebraic quantum field theory, a quasi-free state is just by definition any state whose answer, when you plug into the generator, is just going to spit out the symmetric exponential of the symmetric two-point functions of the thing. Okay, so I hope it looks Gaussian to you, right? It's like an f and f squared divided by 2. In fact, it's like a Gaussian normalized one. Okay, this is just by definition, and this definition is going to be true for squeezed vacuum, for thermal state, and the squeezed thermal state, and a bunch of other things you can construct out of this. Okay. I want to put this is because traditionally, how you define this stuff in standard quantum field theory is that you do a bunch of weak contractions until you organize them into exponentials. But in algebraic quantum field theory, this is just a definition, so you don't have to do anything. Then we are almost done. Okay, am I good with time?
Yeah.
Great. You start with the Stein spring-like representation. Let them evolve unitarily, trace out the rest, and ask what's the final state of B. And remember, we wanted to ask whether B depends on A. Okay, and you just control unitary. The factorization, you don't have to fight time order exponential anymore. And now you replace this with Minkowski vacuum. So the GNS state, you replace it with Minkowski vacuum. And 10 minutes algebra. Like you literally, because all this is just products and linear combinations, right? So you only expand 4 terms, just multiply, simplify, and then that's it. You will just get this quantum channel. Okay. So the left-hand side is quantum channel acting on the initial state of B. And you realize that it is just going to organize yourself into the bit flip term. What's that? Is an asymmetric term that depends on the commutator. But I should point out to you that there's these 2 terms things coming in. Nu B is an exponential of the 2-point functions evaluated on B's interaction region. So this is really measuring the vacuum fluctuations. Okay, why? Because remember, W of F, comma F is actually just the 2-point functions, the vacuum 2-point functions of the field. And so when you evaluate it on FB, it is just the vacuum fluctuations around B. Okay, so this is just telling you how the local noise is influencing the detector B. Now EAB is just my shorthand for the causal propagator integrated around FA and FB. Okay, and now I hope you see what's coming. Okay, first, if you're space-like, remember the causal propagator integrates to 0. Which means the first term just becomes 1 plus nu B. The second term just becomes 1 minus nu B. The third term drops out, in which case nothing depends on A anymore. Okay? So this is perfectly causal. Okay? And second, a nice bonus is that in a strong coupling, when the lambda goes when the coupling strength of the interaction goes to infinity, actually the lambda is hidden in the W, the 2-point functions. So actually, there's lambda appearing for every f you have. So when lambda goes to infinity, this exponential goes to 0. So nu b goes to 0. What happens? The first term becomes half, second term becomes half, the third term becomes 0. What you get is just that in the limit of strong fluctuations, you just have no better thing. You are no better than doing random bit. Okay, does it make sense? So if you are so much noise, you're just no different from just randomly guessing what state it is. And Hagerfeld's problem, you remember his argument.
And it's whether like sorry, how the epsilons and deltas, is that really exactly like random, like completely uniformly random? There's no bias whatsoever, right?
Basically, the exponential goes like it's exponential of minus lambda squared.
Okay.
So if you take the lambda goes to infinity, then I think you can make the bounds, but.
No, but, okay, but my point is like whenever there's some bias away from complete uniformity, then of course you can transmit a bit, just make it a coding thing, right? I mean,
yes.
Make like in quantum error correction or even classical error correction, make a redundant coding, and then if you send enough bits and take a majority role, then you can
I think so.
get a signal.
I think so. Yes.
Okay.
Probably the way I should say it is that depending on how strong your coupling is, then it is harder. The noise basically just erases most of the information, and so it is harder to actually extract which one is caused by which. Now, if you look at Hagerfeld's problem now, he's actually sort of doing something that from a quantum information perspective is kind of weird. Historically, the causal behavior arises because everyone claims that probability of excitation before a light crossing time is greater than 0. But think about it. Even if you are space-like, you still have bit flip anyway, right? Which means that the problem is the acausal behavior they got, they also counted in the problem that the vacuum has noise. And you cannot factor this out in classical calculation because when you do scattering calculations, you're gonna include the vacuum fluctuation. Okay, but essentially the moral of the story is that really expecting the probability to not click at all before the light crossing time is just asking the atom to not interact with anything in the universe. But if you have any quantum field at all, you have a ground state of anything, it's gonna have non-zero vacuum fluctuations, full stop. Okay, so really that's why Cliche and Kemp was asking the right question. You shouldn't be asking that the probability is exactly 0, but rather the probability is completely independent of what A does. And remember, this computation, these two, I didn't have to actually compute anything, right? I just organized this into the definition. But if, for example, if I give you the black hole spacetime, you won't be able to write down how the causal propagator at all, okay? Because right now, even numerically, people are struggling. Same thing for the 2-point function. To do the 2-point function, you also need to solve the wave equation in curved spacetime. So in crazy spacetime, you can't actually write down even the numbers. But here, we got the answer even without doing any single integral at all. So I think I like to see that conceptually, this is a very clean demonstration that you're just causal all the way down to your causal all the way down, essentially. And final caveat, can we ever solve the Fermi problem? Okay, well, if you're Hagerfeld, then the answer is no. Because unless you solve the full QED, which is intractable as of today, then you will never satisfy anyone. In fact, if you look at the 1997 Hagerfeld's paper, he would claim that any model-dependent constructions cannot answer half of what he thinks as half the problem. And I mean, that's fair, but the problem is, do you want to make progress or do you want to wait until someone managed to solve the whole QFT normal, right? But the other alternative, which is what I champion, is the fact that you can use stuff like light matter interaction models like Unruh-Lewin model. It may not be the only one you can use, but in this case, you can actually show that it is fully compatible, not just with special relativity, but with full general relativity. And the quantum information insight really is that, you have to really separate what is non-local correlations coming from the ground state of your many-body system, which is the quantum field theory, from the ones that is coming from signaling due to the propagation. So, you know, in quantum information, even in many body systems, you do have to separate what is information propagation versus the one that is just come from ground state entanglement. And this is essentially the problem. So in hindsight, I hope it is clear to you that, you know, this separation conceptually is a very natural thing that we do all the time. But back then, or perhaps until today, the high energy physics actually are not always very clear about separating this. And I think that's the end of the talk, right?
Wonderful, thanks for the thought. Very fine story. So
Yeah, I think this, I have some other talks that I could give, but I find that this might be the more fun one. And I thought this was good for the morning session.
no, that's good. Late morning.
So the question on the underdrivet detector, I think in one of your slides you showed the space-time integral. And you were
This one.
no, I think it was before that. Yeah, this one. So you mentioned that the underdrivet detector worked for curved spacetimes.
Yes.
So can you incorporate fluctuations of the metric here? So if I was doing like something like a gravitational path integral.
To be really honest, I'm not sure. So far in the literature, there's only one paper that tries to do path integral description of an underdrivet model. And they find that the path integral description of the underdrivet model is a little bit looking more like a line defect. But I don't understand what that is. It's like a Wilson, it's like a Wilson.
Yeah, sure.
But I'm not familiar with that. But right now, this is about the state of the art, because part of the problem with relativistic quantum information right now is that we are still stuck in the regime of fixed background. So if someone makes a progress in that direction, I think that would be very interesting. But right now, I have not seen
But
it.
this is like, I mean, you're basically asking like for a theory of quantum gravity, right? More or less.
Well, no, not necessarily. You could do like some classical gravity because that's what the gravitational path integral is.
And also there's another one, for example, if you do what we call the passive quantum gravity, which is like a stochastic noise on top of the passive automatic.
I see. So that would kind of reflect some back action of the quantum. So
That's right. It might not reflect the real quantum gravity, but it will go beyond semi-classical.
I see.
I'm wondering how strict your assumption that the Hamiltonian the interaction acts instantaneously is, in the sense that what I could be worried about is that you require instantaneous interaction. Such wouldn't you have the issue that either you can introduce lots of noise, like you see, like you can have a lot of fluctuations on these ends if I act very strongly,
Yes.
very short time, and if I don't act very strongly, then I don't really do anything.
Yes. So I haven't found a satisfactory answer to this or heard anyone doing this, but actually I thought about it last week and I think I got the answer, but I don't know how many people I can convince. And it is exactly your problem. Actually, not last week, quite some time back. But you're right. Like if I make a sharp interaction, right? Normally you would introduce so much fluctuation that you cannot measure anything, right? But remember that this intuition comes from people thinking of atoms or quantum systems as a point-like object. If you take a point-like object and you take a delta time, then you are essentially evaluating the field at a single point, in which case the noise is super big. But remember, in quantum field theory, you need to smear it in space and time. Okay, and so long as the interaction has a spatial extent, there's going to be a stronger ultraviolet cutoff than the delta interactions. So one way I can convince you this is the following. Where is the causal propagator? Here.
Yeah.
This is a Green's function, right?
Okay.
So it is a Green's function, which means that it is like a delta function. It will diverge at a point, right?
Yeah.
In a delta time interaction, this still diverges, right? But if F is like a Gaussian in space, but delta in time, this integral converges. And this is actually the source of the singularity of the Weigmann two-point function.
Mm-hmm.
So whether something introduces how much noise, eventually, from the perspective of quantum field theory, how much noise means you have to compute the two-point function of the field with respect to any F and G you pick, and then check what's the number. And for the delta interaction, with with finite spatial extent, the answer is finite, and it's not big, depending.
So could you, for instance, compute the, or say something about the capacity of this channel for times that are bigger, longer than the causality line, and say that even with delta interactions, you could still convey lots of information through this channel? That would be.
This paper comes after my previous paper, which computes the channel capacity of this paper, the classical channel capacity, and I show that it is 0 at spacelike.
Yeah.
It is 1 at the non-separated one, and since I'm using master scale field, it is also 0 on the timeline direction. So I did compute that. That's paper.
So, but that's in the same model, right? So
Yes, it's in the same model. So the channel capacity is 1.
Well, that's really interesting. That means that indeed, if you, by acting instantaneously on either end, you are able to kind of
Exactly, you can. And in fact, there's an asymmetry going on. Alice has to couple strongly to the field, but Bob has to couple weakly. Yeah, and that has to do with the fact that if Alice has to put a lot of effort to inject classical bits into quantum field, but Bob cannot interact too strongly relative to Alice because otherwise Bob's noise is going to overpower the classical bit. Once you find this balance, the channel capacity is going to be 1.
Okay.
And in fact, in flat space-time, the quantum channel capacity of this kind is also found to be 1. But the coupling has to be modified a little bit. So actually, we do have relatively quantum channel with maximum quantum channel capacity. And right now, part of my project, which I kind of like trying to work with Jens, is part of the proposal is to generalize it to curved spacetime, and I think it's kind of trivial.
But speaking of which, I mean, it makes perfect sense to really speak of this as a communication channel, right? I mean,
Yes.
One could in principle define a whole capacity and so on.
Exactly.
Channel.
So,
I mean, in fact, for the bounds and bounds, has been done, right? I mean, people know, I mean, the way it's formulated is a bit funny, but you can easily see that you take a hammer and put something here, and then you ask, is there a signal far away? And outside the cone, you get exponentials pressed. And
exactly.
that's kind of a kind of detector model, but you can really see this as a classical communication channel where the bit encoder takes the hammer and does Morse coding, and then that has a capacity, and the lead bounds and bound will also upper bound the hollow of this channel.
Exactly. Although, as usual, classical channel capacity, even classical channel capacity is normally hard to compute, right? And this channel, the channel defined this way, the delta interaction at one instant of time, has the lucky behavior that it is entanglement breaking. So the level channel actually the n copies product reduces the signal. So
you can imagine doing kind of other things like instead of computing the capacity is hard to compute, but you could look at some diamond norm to some constant channel or something like that.
Yeah, I wish.
Besides, I mean, let's not forget. I mean, most of this is like saying that you can't do it, and then the asymptotics goes the nice way around, right? I mean, just don't regularize it, and you're still a business, right? In a way, the one copy formula says a lot, even because you want to say that you can't communicate.
In any case, I should say that the first person who came out with an actual computation of relativistic quantum channel in this kind of non-perturbative regime, that was 2016. So you can see that we are sort of like 10, 20 years behind the standard quantum information. So everything you propose about diamond norms and everything else, probably no one has done it. I mean, my channel capacity paper that I just told you, that was February this year. So we are really lagging behind. So either people outside the field has to come in to kind of push this forward, or someone else has to find another thing, because we are really lagging behind this. Anyway, that's.
I don't want to monopolize questions.
No, go for it.
We would have another one.
No.
Jens mentioned Lieb-Robinson bounds. You use this type of argument to show Lieb-Robinson bounds in systems where you have kind of I guess you have unbounded Hamiltonians where the standard proofs of Lieb-Robinson bounds don't work. That would be the situation here where you kind of really show operationally that you cannot convey information further away.
You're going to discretize it. That's funny because the converse is kind of, I mean, a baby version of the converse is true. And we had a paper about it like a million years ago, which says that you take a harmonic chain, and harmonic systems have unbounded operators, obviously, but they still have Lieb-Robinson bounds.
Yeah. You
can show this, not so difficult. So they're in fact in this precisely the same sense. It's just formulated in a very different fashion. But then you can take these lattice models and take the continuum limit to the non-interacting Klein-Gordon field, and then you can say what happens in the field limit. And then what happens is that the cone becomes sharper and sharper, and you really get the exact light cone of relativity out. So you can basically derive relativity from Lieb-Robinson bound. That's basically your program, but with the arrow the wrong way around. I've derived relativity from Lieb-Robinson bounds, but you want to derive Lieb-Robinson bounds from relativity, right? From causality.
Maybe I'm confused because I'm mixing things up. But if I remember correctly, if you have unbounded, like if you have Hamiltonians that are unbounded, typically your Lee Robinson bounds would give you, it depends on the norms.
That's what I said. You have to formulate it differently because if you put it gives you infinity. The infinity is more than infinity. It means nothing because the operators have no operator norm.
Right.
No, but you would formulate it differently. You would take it. I can show you. There's bounds on. You would express things in terms of moments. And then the moments are just fine. And then you have to get the same thing. There's a cone, the speed of sound, and outside the cone is exponentially suppressed. Everything is physically the same, but the way it's formulated is on in terms of moments of states and not of operators evolving in the Heisenberg picture, because as you say, that means nothing. So mathematically very different, physically identical.
Yeah, but also I should mention that in the operator language, right? I think if you believe in non-interacting theories at least, right? You can always construct the Val C-star algebra and do the Lee Robinson on exponentials or equal operators. And this is what someone did, I think.
How does one believe in non-interacting theories? What's the belief system and what's the?
Oh, no. I mean, like it depends. I have talked to some people in the past, and to them, like quantum theory is all about particle physics. So it's not.
Of course. Yeah, but in condensed matter, you have to be really careful to speak about non-interacting systems and not have like a 20 disclaimers that you're saying something very non-trivial, because otherwise they will eat you up alive.
Yeah,
it's very, very interesting.
Yeah, unfortunately, I'm not a content matter.
No. It's kind of funny because this is just a cultural thing, because like the problems typically stated in that setting are just would then be very simple if you had a non-interactive system. It's kind of interesting how these cultures are.
But to follow up on that, what is the role here of interaction? Like,
Sorry?
What would be the role here of interactions if your field is not free field?
Essentially, this is the region where you assume that the interaction. So you have an interaction. So the field is free. The qubit is technically free on its own, and then you do an interaction here, right?
Right.
So actually, there is a hidden, very deep mathematical subtlety that we are like throwing under the carpet, which is that I'm solving everything, pretending that the Hilbert space is a tensor product of a free Hilbert space.
Right.
I mean, the real solution, the real full QED solution for this, even in this context, would be that take the qubit, take the field, find the full joint interacting Hilbert space, in which case the qubit and the field are both dressed vacuum and dressed ground states and stuff. And you have to like renormalize everything in principle, but no one knows how to do this. And this is basically the mathematical problem of finding the C-star dynamical system of a particular interactions. And this is an open problem for most quantum systems of interaction. The only solvable ones I know, I'm not sure if this is something that people do in condensed matter, it's called the Van Hove model. It's called the Van Hove, where you basically take a quantum field interacting with a classical current. In which case you can show that the Hilbert space of the interacting theory is actually different from the free one. But that's the only one we actually have a proof, like a mathematical proof. Yeah, the rest is okay.
So here the interaction between the qubit and the field is not relativistic.
Oh no, the interaction itself is relativistic up to the internal dynamics of the qubit. So for example, you might notice that in the interaction Hamiltonian here, right? I prescribe this shape, and I prescribe the poly X and sigma and the field, right?
Right.
But if you think about it for a second, imagine the qubit is actually the first two levels of a hydrogen atom. Hydrogen atom is not relativistic, right? So how can this be a covariant relativistic interactions when I'm using non-relativistic one? Well, the answer is we have a marker.
No, there's a red marker on top of the piano, I believe. That should work.
I'm not sure if I should use this, but in any case, basically the point is that if the qubit is of this size.
You can send people to Mars, but why is it impossible for humankind to have tensors that work? We needed Mars to sort out this thing first, right?
Oh yeah, I'm doing something wrong.
It's right.
So if you think of the interaction with the block, in which case the delta interaction means you are kind of like a strut, right?
Yes.
This whole thing is fully relativistically causal up to this scale. So that means propagation of information of this kind is causal, but there is something acausal if you put them to only pass through partially. And this has to do with the fact that if you want to talk about causality of these two models, right, you have to kind of put them in the appropriate place up to coarse graining. And the reason is because if you only pass through half of it and you don't pass through the other half, you are like crossing half of the hydrogen atom, but half of the hydrogen atom is not relativistic. So in this region, if you get some numbers, you shouldn't really trust it. You should put them into here. So this is the limit of the model. It's like it's the price you pay for using non-relativistic systems.
Thanks.
I'm not sure if my question makes sense, but is there a way of understanding how much the role of the vacuum state having some entanglement plays in this argument?
I mean, that's the big question. In fact, that's also in my Humboldt proposal. It's like the problem right now is that I'm not sure if you have heard about this protocol called the entanglement harvesting protocol.
Might have.
So basically, the idea is similar. You take two qubits. It doesn't have to be delta interaction. Interact with the quantum field, and then they will extract entanglement from the quantum field, and you ask what's the amount of entanglement you got from these two qubits. Now, the problem is, if you only do perturbation theory, you only get very, very small amount of entanglement. So, but the quantum field, as far as we know, has infinite amount of entanglement because it has a very strong ultraviolet structure, which means that most cases, this kind of coupling can't tell you anything. But I have an idea based on the fact that if you do some kind of similar modified coupling, you can do non-perturbative entanglement swapping with the field, and whatever imperfection will tell you how much entanglement you get. And now the question is, what's that number? Because no one computes that number. And in quantum field theory itself, people only know bounds, and the bounds are loose. That means no one knows how to separate any of those bounds.
Couldn't you? I mean, I realize this is certainly not rigorous as an argument. Like, couldn't you say that if I have, I could look at the system at some fixed energy scale, right? Maybe.
Sure.
And that already tells you can't extract infinite amount of entanglement from the vacuum state. And then look at states where you have your atoms further and further apart, and you'd expect this amount of entanglement to decay exponentially. So could you see, and maybe longer times, could you use that to say that basically this this causality really comes from the internal dynamics of the Hamiltonian and not from the pre-existing. Hence, the pre-existing entanglement doesn't really help.
So this is really a bit tricky because the problem is whatever entanglement you get, you don't know if it is entanglement because of the interactions or it is coming from the quantum field, right? Because entanglement is not conserved. You can't say A plus B plus C equals to the original one, right? You are right that if I bring qubits far away, the entanglement, if they get entangled, they are going to decay. But that decay is not always exponential because the 2-point functions of the quantum field is polynomial decay. It's an algebraic decay. Because the decay of the correlations depends on the 2-point functions of the theory. So exponential decay means that you have to do something. For example, if you are in a thermal state, if the field is in a thermal state, then the 2-point function actually, I think, has an exponential decay that goes with the e to the power minus beta.
Right. Sorry, if I have a vacuum state, don't I have for two space-like separated qubits points? Don't I have exponential decays of 2-point functions?
No, because
it's like a thing to BCFT. It's like phi x, phi y. Compute the 2-point function of that. It's going to be 1 over x minus y to the 2 delta.
Yeah, I need to look it up again.
Yeah, this whole exponential decay thing is a bit subtle because like for example, when you do open quantum system with this stuff, a lot of stuff about Markovianity requires exponential decay, but that never happens for this inertial qubits in the vacuum state, in which case you will never have Markovianity, for example. So this stuff you have to be careful about the 2-point functions.
Wonderful. That was good. Good discussion.
Thank you.
I think let's end the formal part here. Thanks again for this inspiring talk. Thanks to everyone for the good discussion. And then we also end the recording. Oh, too late.
Right.